course, today we are going to be covering yet another interesting topic, focusing again on space, where we're going to be talking about ring worlds and ring structures. Now, we're going to be covering a wide variety of scales here, going from smaller ring structures that we might be building in the near future, all the way up to gigantic Niven style ring worlds that encompass the entire orbit of the Earth. We're going to be talking about how feasible these are, why you would or wouldn't want to build them, and what life is going to be like on such a structure.
Yeah. No, it's should be an interesting topic.
Okay, so I figure if we're going to be talking about ring structures and ring worlds, a good starting point is to start talking about how spin gravity works, right? Because that's typically why we talk about building a ring structure.
Yeah, and it's also the biggest challenge that we'd face with constructing these structures and living on them.
Yeah, absolutely. So it is really important to note that when we are talking about these ring structures, again, we're going to be spinning these for gravity. I think this is something people are fairly familiar with. It's been discussed before when we were talking about O'Neill cylinders in episode, what was that, 2 or 3? It was an early one.
It was a long time ago.
Yeah, it was. So we talked about it a bit then, but I didn't really dive into the challenges that come with spinning a structure for gravity. The biggest thing is on the smaller scale, right? There is a limit on how small you can build these structures because at a certain point, as you go smaller, the actual amount of times that you spin per minute, the RPM, goes up. So
Right.
if you get to too small of a state, right, too small of a ring or a cylinder or what have you, you end up feeling like you're in a washing machine. You know, you're flying around in circles, and it leads to a lot of nausea and vertigo, and you're not going to feel well.
Yeah, like imagine you would be in a hamster wheel, a human-sized hamster wheel, and trying to spin it fast enough to where you could stand flat on your feet. It would be incredibly disorienting. And yeah, that would be horrific.
Exactly. And then that's also another issue too, is not only do you have the issue you're spinning around a bunch and that's disorientating, but you get a really strong difference in force between your feet and your head when you have a
Mhm.
smaller structure. For example, if you're in a 10 meter in diameter structure and you're spinning that around, which will probably be spinning at something like 20 to 30 RPM, then you're going to be feeling almost a third less gravity on your head than on your feet. And that's going to create a bunch of disorientation. It's going to feel weird. It's going to feel funny. And then also, if you were to like stand up on the structure, because you're going to feel this difference in force, then you would actually feel a lateral force that almost pushes you over on such a small ring.
Yeah. Yeah, because as you're getting up, those forces of gravity are applying on different parts of your body as you're trying to stand, and it would not feel correct unless you were perfectly straight up and down.
And even then, you would feel a difference in force between your feet and your head.
Oh, yeah.
So, this is all to say that you need to go at least a certain size. If you go too small, it creates issues. And of course, if you go too large, you fix the issues with spin gravity, but we come into material constraints, and we're going to be addressing that a little later in the episode when we talk about these bigger spin structures, and we're also going to be talking about how you can overcome those challenges and deal with it. But I will also add that there are other things that we can control other than the size of the structure and how fast it spins. So I mentioned there is a limit on how small you can go before you start to feel sick. And by the way, for reference, we think that's around 2 RPM. Most people can handle about 2 RPM and feel just fine. There are some papers I've seen that say that people can adapt as high as 4 RPM, but then at that point, you really need to have like specially trained people, and this probably isn't going to be for the general public.
Yeah. And I mean, when we're thinking of a structure that is spinning at 4 RPM to create 1G, like what would the size of a structure like that be?
Yeah, so I know a 1 RPM structure or 2 RPM structure with 1G is going to be about 128 meters. So with 4 RPM, you can half that size. So you're going to be about 50 meters tall. So about twice the size of this building.
Yeah, I mean, when you get to the point of you're spinning a structure that's 50 meters in diameter, like what are you even achieving on a structure of that size?
Well, the advantage to that is you can build smaller. And so that could be hugely beneficial. Although this was the second point I was going to bring up. The spin and the size aren't the only two parameters we can change. We can also, of course, change the gravity. So, for example, if 4 RPM is too fast for you, but you want to keep your ring structure the same size, maybe that's as big as you can build,
Mhm.
you can also just half the gravity. You can make it a half G instead of a full G, and then all of a sudden you can drop to 2 RPM, and that could be comfortable for the inhabitants. And this is something that we've talked about before, I think in our moon colonization episode,
Mhm.
is that the only catch to that is we really don't know how much gravity humans need to be happy and healthy.
Yeah. I mean, that's definitely true. Like, really, my only frame of reference is on Interstellar when they landed on the planet, and they were like, it's very comfortable, it's 80% of Earth's gravity.
And 80% of gravity might very well be comfortable. That might be perfectly fine. And you might see a lot of these spin structures lowering their RPM and using 80% gravity is a happy median to save a material strains. Or maybe 80% gravity isn't strong enough and we really do need to have exactly 1G for humans to be healthy. Right now, we just don't have the data. We know that 0G isn't enough, right? Like we have tons of data on microgravity from the ISS, but that's it. We know 0G, we know 1G. We've had 12 human beings in all of history who've existed in any other gravity than that. Those were the Apollo astronauts, and then they only existed in those conditions for a couple of days at most. So we really don't have the data to say if anything other than 1G would be enough for human habitation long term.
Yeah, I mean, it could be detrimental or it could be beneficial. That would be exciting to see. And with the construction of ring worlds like this, we would be able to experiment with that further.
Yeah,
So,
absolutely. So that's something that we'll have to do going forward as we move into and colonize space. But yes, I just wanted to bring this up as a third lever we can change, right? It's not just size and the RPM, but we can also control the surface gravity if that ends up being enough. And for my part, I think 80% gravity will be totally fine for humans or even most mammals. Even as low as 50% might be fine for shorter term habitation. And you can also get around this. You could potentially have a ring itself that experiences 50% and then extend off of it rooms attached by tethers that go out further that it maybe experience a full G or exercise and maybe even sleeping if it turns out that sleeping in lower than 1G is not comfortable.
yeah, that's the first thing that I thought of when you said that you could have rooms that were living at 1G. It's like your workspace could be in a lesser G because that makes working incredibly easier. But then you go home into the comfort of one gravity.
Yeah, and it wouldn't surprise me if we started seeing these for space tourism, if that's how they were set up. Might very well be a case that the actual ring itself is in lower gravity, maybe 50%, maybe as low as 25% to give the novelty and the fun and allow people to experience lower gravity. But then you have habitation sections extended off of the ring held by, they could be tethers, they could also be essentially elevator shafts, and that allow people to live and work in 1G where they feel comfortable. And you don't need just two of these. As long as you have them opposite sides of each other so that they're balanced, you could send these off as many as you want, like spokes off of the main ring to have a bunch of rooms like this. So I could see a space hotel having this situation where the rooms are held off on tethers to be 1G, and then there's a central like entertainment area that's half G. Or you could even have multiple rings experiencing multiple different gravities. Maybe you have one ring for moon gravity, one ring for Mars gravity, or what have you. So lots of options with these rings to vary the gravity if that's what you choose to do.
I can see it now. A trip across the solar system, all in one hotel.
And then you have the room that's held by a tether that's as long as can be to experience sun gravity.
Oh, God.
Lots of different things you can do with these in the near term to change the gravity and change what it's like living with them. But let's actually now change gears a little bit and talk about how big of these we would actually reasonably build and what living in them is going to be like. Now, one of the first examples of a ring structure is going to be something like a Stanford torus. Now, I know I preface this with ring worlds, which we'll get up to, but a Stanford torus is a much more reasonable ring structure that we can actually see ourselves building in the near future. So this would be something akin to almost like an O'Neill cylinder. I remember we talked about those. I referenced that before. It's going to be a couple of kilometers in diameter, between 2 and 6, maybe up to 8 or 10. Really depends on what materials you're building out of and how much you want to push those materials. So the Stanford torus was designed back in a time before we had advanced carbon composites or things like carbon nanotubes on the horizon. So the entire idea of the Stanford torus was built around using things like steel and iron. So it's designed to be used with those materials. And it's something we could, again, really build today if we wanted to. Like we have the materials for it. It's just the question of getting those materials up to space and actually building this thing.
That's a great starting spot because that is something that is very approachable with the materials that we have and still seems very livable. I've seen many examples in science fiction where people are living on stations that are about that size where you can kind of look up and see your neighbor's house above you, wave to them.
Yeah, that is the question, right? Yeah, you can look up and see your neighbor's house, but that actually could be an issue with privacy, right? I don't really know if I want someone looking up and seeing my house.
Yeah. Also, you have that weird point where if you throw something high enough, where does gravity shift and then it falls?
Yeah, so for the Stanford torus, I don't think you physically could throw something high enough. I just don't think you have the strength to do that. I don't think you would be able to reach escape velocity off of it. But, if you had a gun, for example, that potentially might have the power to actually send something to the other side of the ring. But I guess that's not really any worse than shooting something up in the air on Earth, right? I think it would still be the same liabilities there.
Absolutely.
But that
Yeah.
would be an interesting assassin movie, having to like line up a sniper shot across the ring, and it'd also be crazy because the bullet would take like an S-shaped path as it moved up across the ring.
Yeah, it would
Be a
be
very complicated shot.
sniper school would have a whole different like schooling system to
Yeah.
it now.
But yeah, no, I do agree with what you said earlier. The Stanford Taurus makes a wonderful starting place for moving out into space because it's smaller than an O'Neill cylinder, which makes it a lot easier as a first habitat to build, but it takes advantage of being that same size and radius so that you still get all of the spin gravity benefits and you don't have those really strong Coriolis effects that you would have in a smaller structure. And that's really where I see these being used more than anything.
Yeah, it's that first step of comfort
Yeah.
in space.
So these are typically designed by, of course, being a rotating ring, if you can imagine, with the people living on the inside of this ring, and then it's going to be capped. Now, I know in the original illustrations for this, the cap was some transparent clear material like glass. I think that's probably what they used back when they designed this, and then you could see through to space or to the other side. And that
Right.
is actually really important to make up with these Stanford Tauruses. They are not big enough to contain an atmosphere. You do have to close them off. They do have to be a pressurized cylinder. Now, whether you want to make this a torus, like a donut shape with a hole in the middle that's open, or you want to make this almost like a disc and close all the way up to the middle is up to you. You could do both. For my part, I think something this size, the torus shape does make more sense. There's not really any benefit in building it like almost like a flat disc unless you just wanted to.
Yeah, the only reason that comes to mind is like you were saying before, you could build one like that for maybe tourism.
Yeah, that is possible. You can have multiple floors, and that's definitely something you could do. And I could see that being used for it as well. But in general, I think the torus shape itself makes sense, especially if you have the desired gravity at your rim. And then also, like I said, the original design for this had an open top so you could see out into space. The issue with that is that these still rotate quite fast on the order of 2 RPM, depending on the size you go with. So you're not really going to want to see into space, and you're definitely not going to want sunlight to shine into it, or you're going to have a day night cycle of, well, 2 minutes, right? That's going to be very annoying. It's going to be very hard to sleep with the sun flashing up every 2 minutes.
Yeah, not to mention the vertigo when you look up and
Yeah, you're just flying around in
spinning
circles.
around.
Yeah. So I think it actually might make more sense to completely close the structure. And instead of having glass, you could just have a completely closed off tube and then have an artificial sky, perhaps with LEDs or displays, kind of like how we talked about doing with an O'Neill cylinder. Or if you do really want to have that open, clear glass top, what you would probably do is put these rotating in line with the sun so that no sunlight shines into the ring. And then you could put a mirror in the middle rotating almost with it with just a slightly slower rotation to simulate a day-night cycle. This mirror slowly spins and flashes light on every day or night. Or you could just have a mirror and then angle it when you want your day and angle it away when you want your night and just do that in a 24-hour cycle to simulate a day-night cycle if that's what you want.
Yeah, which of course those applications would have their positives and negatives. That being that they would be a little bit more complicated to set up and expensive in the structures. But if you did do that, you would be getting natural light and you could grow crops and things like that. But we've talked about doing that already.
And I actually don't think
before.
these would be that much more expensive. The mirror can be a thin foil. It can be as thin as paper, if not thinner. So it doesn't need to be complicated. Really, the only complication is going to be having the clear glass cover
Right.
versus having like a metal one. But even that, I don't think is too bad. We have materials that are more than strong enough to handle that.
Okay. I would definitely prefer that option then
Yeah.
over LEDs. It feels like you would just get sick from it over time.
Yeah, maybe. I don't know. Maybe at this point you could do a perfect 4K or 8K display and not even be able to tell the difference from a real sky. I would expect LEDs to get cheaper in display technology like that, especially how much money it's going to cost to build one of these structures anyways, right? Like the 4K display to simulate the sky can't be a huge cost in comparison.
Yeah, no, I mean it would be awesome. Like on holidays, the entire sky just like lights up to be festive for whatever section it's in. But
Or someone's going to run Doom on it.
of course, I was the first one to run Doom on the sky.
As for living on a Stanford Taurus, it's going to be pretty similar to an O'Neill cylinder. These are smaller, so instead of housing tens of thousands to millions of people, you're going to be in the low thousands range, depending on the population density you want.
Yeah, I mean it definitely makes sense. Like it is at its core. I feel like the first step to an O'Neill cylinder. It is the modular start for it.
Yeah.
Because you want to continue to expand it, you would expand it in a tube-like fashion, in a three-dimensional space instead of it just being a ring. But it's great to talk about them because this is where we would start.
Absolutely. Like you said, it could be a great start. You could expand them out long ways and end up with something like an O'Neill cylinder. Or, I could see these being built for space stations where you just don't need that many people,
Mhm.
right? Like an O'Neill cylinder could potentially have the land area of a city. And you might not need that much area. So you might have a smaller corporation that says, oh, we just need like a ring structure like a Stanford Torus. That's perfect. That can house all of our people and have our manufactories.
Yeah. That's actually interesting to think about. Like just like corporations building, just like these rings out in space to do different types of heavy lifting production or logistics, and just have them, floating out there and set up. That way, it doesn't have to be so expensive or formed by a government or by the entire planet itself to have that started.
Yeah.
Once that technology is done, just throw a couple rings up there and get your company started that way.
Yeah. It seems like a much cheaper option than like a cylinder. But cheap isn't always, I think, what we're going after. So let's talk about scaling these up. So the Stanford Torus is, again, I would say, analogous to something like an O'Neill cylinder, being a couple of kilometers in radius. Taking that to the next extreme would be something on the scale of a bishop ring.
Okay.
So bishop rings are typically talked about being around 1,000 kilometers in diameter. And for this size, we really do need a super strong material, something like carbon nanotubes, which is actually where these were created. So we had the idea behind an O'Neill cylinder and a Stanford torus, and then new discoveries were made for things like carbon nanotubes. And so some people decided to design around those and scale up the Stanford torus and O'Neill cylinder, and that gave us something like the Bishop ring and the McKendree cylinder, which are just the bigger brothers of the aforementioned space habitats.
Right.
So these Bishop rings are, like I said, on the scale of 1,000 kilometers in diameter. And the interesting thing about these is that they're actually big enough that you can trap an atmosphere without entirely closing off the structure. So you can build rim walls that are a couple 100 kilometers high, and that's high enough to actually trap an atmosphere and have atmospheric pressure and potentially have even less atmospheric leakage than the Earth has. And then you can literally just fly into this thing from space and land on the surface if you so desired.
Yeah, that's insane. It's like setting up an atmospheric wafer.
Yeah.
But that is an incredible concept, though, because that pressure, of course, would want to stabilize itself within that ring.
Yeah, exactly. The ring spinning throws the atmosphere against the side, just
Hmm.
like it would throw you. That's why we spin these to get gravity. And a couple 100 kilometers high, 350, 400 kilometers high, is more than high enough to trap an atmosphere. I mean, I don't even think our atmosphere, I mean, it technically does go that high, but you're way below atmospheric pressure at that point. And it's going to be about the same stratification as Earth's atmosphere. So if you imagine being 400 kilometers up on Earth's atmosphere, there's hardly any air there. So the
Yeah.
leakage is so minimal. And like I said, it can actually be less leakage than the Earth itself if your rim walls are built this high.
Yeah, that's pretty crazy to think about. Like being able to produce an artificial atmosphere and then use the spinning to make it even more efficient, have no leaking. It just proves more and more that living on planets is obsolete.
Yeah, right. And I mean, that's the main thing, right? With these bishop rings, you're getting into like continent sized habitats, or you can support tens of millions of people, but you can make hundreds of millions of these with the same mass as a planet. So if you take Earth, not saying we should take Earth and dismantle it, but if you did take the mass of Earth and dismantle it and build these, you get way more living space than you have on the Earth itself.
Well, of course, yeah, because it would just be more efficient. You're taking all that inner surface area of a planet and just spreading it out across bands throughout space. But all that harvesting and taking in all those resources to do that is an incredible undertaking.
It is, but when we're talking about building on the scales of Dyson swarms and even some of the other structures we're going to be talking about there, it's not undoable. It is
No.
possible within the realm of physics. Yes, it's a lot of work and it requires a lot of energy, but thank God we have a humongous nuclear reactor in our sky that we can harvest for energy, and a couple of planets that we're not doing anything with, like Mercury and Mars and even Venus.
I mean, really, when you look at it, it beckons for it.
It does, exactly. And these are huge, right? So these bishop rings, for a bit of scale on these are about the size of the Halo rings in the Halo series.
I mean, some of the Halo rings they vary in size, but I'm sure everybody out there can remember the first time you loaded into Halo and you look up and you can see the whole ring going from one side to the other. God, that would be incredible.
It would be. I do think some of the larger Halo rings are about 10,000 kilometers in diameter, but that still would really fall into the realm of a bishop ring. These can vary a lot.
Yeah.
And then I mentioned having the rim walls, right? I think for living on one of these, you would probably make the rim walls look like giant mountain ranges coming up on either side.
Yeah, because it would concave in kind of, right? On the rim walls, it wouldn't just be like a straight. down.
I would think you would build them like mountain ranges that drop off pretty quick. This would be something like a very steep mountain range because you don't want to make a bowl. You can make a bowl, but that's going to make all of your water rush to the center of your ring and potentially have thicker atmosphere the middle of your ring than on the sides. So I imagine you want a flatter bottom with pretty vast mountain ranges coming up off the side,
Yeah.
something like the Himalayas.
Man, okay. It's just to think of the scale of that for a second. Like we are building a structure that inside of that structure, we are building some of the largest known land, like natural structures on Earth, just to cover up the sides to make it look better. Insane, absolutely insane when you think about it. But I absolutely agree. You would want that to look more natural, but you wouldn't want it to concave. I was originally thinking that because, gravity would naturally want to flow that way, but we would want to counteract that for the reasons why you mentioned. We wouldn't want to just flood the middle and then, have the sides be.
Or you could potentially do that. That would be an interesting feature. You could have a giant ring ocean that goes around the center of it and maybe have a bunch of coastline on either side of it. That could be an interesting design and maximize coastline. That's what people love. So I'm not going to say we wouldn't do that. It's just that if you did do that, you have to keep in mind that you are going to have a natural pooling of water toward the center.
It's like even in space, everybody's trying to get beachfront real estate.
I will say for my part, I don't know if you would really do that. I imagine a better design would be something like a bunch of small, shallow oceans or lakes, really, breaking up the habitat. That way you don't just have a giant ring ocean taking up a bunch of potential real estate. Much better to make a bunch of isolated pockets of lakes and smaller, shallow seas to maximize that real estate and change the variety a bit.
Yeah, of course, because you would want to have a natural look to it, but just like flooding the middle just doesn't make sense because then you have to do it for the entire ring as well. It really takes away from that. But
Yeah. And you do want water, by the way. That's worth mentioning. Not only does that look nice and people like to live on coastlines, but when you have water, that will drive evaporation and you'll get natural weather cycles versus not having water, then you won't get a rain cycle and you won't get weather.
and I imagine on these, just like in Halo, you would have ecosystems, plant life,
Absolutely,
things
yeah.
like that to support your atmosphere. So you would need a natural water cycle like that to function.
And because, like I said, this isn't a pressurized tube, it's open to space, you're going to get a normal atmosphere effect. You're going to have evaporation rising up, turning into clouds at a lower density, turning into rain. So you'll have natural water cycles.
Now, how are we affecting the day and night cycles on these?
So it's the same trick I mentioned before. You take a mirror, you put it in the center, and you use that to reflect sunlight in to make a day and night cycle. And if you imagine this mirror reflecting light from the sun into the inner ring and slowly moving that light across the surface and just have it make one rotation across the ring in 24 hours, you would effectively simulate a day-night cycle.
God, that's just so incredible to think about.
And it is the same situation as the structure I mentioned before. You're not going to want to expose it directly to the sun because it's spinning too fast and you would not get a 24-hour day-night cycle.
But you could have it be whatever cycle you wanted it to be.
If you do the mirror trick, you can do whatever you want. You can do 24 hours, whatever you want. But like I said, this does rotate faster than once per day.
Of
So
course.
you would need to do a mirror or some type of trick to get a day-night cycle.
Yeah, and I understand that you couldn't just use the sun, but
Well-
I'm saying you could manipulate it to be, a cycle in whatever way you wanted it to.
Absolutely. And you could just use the sun, but that actually gets us into this next order of magnitude of structure, something called a Banks orbital. So a Banks orbital is actually named after Ian M. Banks in his first book, Consider Phlebas, which is part of the Culture series, which I know I've told you I've been reading this
Yes.
series. So I was very happy that it's one of the things that drove me to pick this topic. So a Banks orbital is designed so that it generates 1 g of gravity, apparent surface gravity, but it also takes one full 24-hour day to do a rotation. And the advantage of building it like this is that if you actually imagine a ring, right, in line with the sun,
Right.
one of the walls would put the other one in shade. It'd be permanently in shade. Now, if you were to take it and put it at a bit of an angle, the wall furthest from the sun would be exposed to sunlight. So now, if you have a habitat that rotates once every 24 hours, you have a 24-hour day-night cycle. And that's the idea of a Banks orbital. You just put it at an angle, and that way you have sunlight hitting on the interior surface of it, and then the other side is shaded because it's facing away from the sun, and it takes 24 hours to rotate and gives you your natural day-night cycle. And you can even do seasons if you want. If you have, instead of a perfectly circular orbit, you do an elliptical orbit around the sun. As it gets further from the sun, you'll generate a winter season. As it gets closer to the sun, you'll get a summer season. Now, the weird thing about that is you'll get 2 winters and summers per rotation around the sun. So you'll have, instead of a year calendar for your seasons, you'd have a 6-month calendar. But it would still give you your seasons. And also the whole orbital would be in the same season at the same time. You wouldn't have seasonal variability like you do on a sphere.
Yeah, I mean that's pretty incredible. I feel like that would be in my mind, like that is the top tier.
Yeah, that is the ring world, right?
Yeah, like that is what people think of when they think of, the ring world. The only question that comes to my mind though is the essentially artificial atmosphere that's being produced the same way that it was on the other rings,
Mhm.
I imagine. Is that enough to block the UV radiation the way that our atmosphere does?
Oh, absolutely.
Hmm.
Because it'd be the same atmospheric depth in terms of spinning it in terms of gravity. You would, of course, need something to block the electromagnetic radiation. That's pretty trivial to do in comparison to building these orbitals. And it is worth mentioning that our atmosphere blocks most of the harmful radiation from our sun, more so than our magnetic field does. But again, you can put an artificial magnetic field up to block some of that from the sun and still get the exact same safety we have on the planet.
Insane.
There is, of course, a drawback to doing a Banks orbital. Well, I don't know if you want to call this a drawback. It is a ring world, and I really do want to do emphasis on the world. These things are massive. They're huge. So for Earth-like gravity, you're gonna be millions of kilometers in diameter. Just to put that in perspective, a Banks orbital could go around the sun. It is bigger than the sun.
Oh.
Now, you would not put this around the sun because it
Right.
would be way too close and it would kill everyone. It'd be way closer than even Mercury's orbit.
First ring oven.
Yeah, exactly. So this is not something you're going to put around the sun, to be clear. You would
Right.
put it in Earth's orbit or around a similar distance as Earth, but the structure itself is larger in diameter than our sun is, has a larger circumference than the sun does. And that does have some drawbacks.
Okay, so when I think about that, then if it could orbit the sun, if we had it spinning and it was getting sunlight directly from the sun, wouldn't that be like such a difference in distance, like from the back of the ring to the front? If you're getting normal feeling sunlight on the side where you would be receiving it, then the back hitting that ring would be like cooking. Because
No,
it'd be
not
so much
really.
closer to the sun.
Not really, not when we're talking about the distances. So, 1 AU from the sun is about 93 million miles. So you're only a couple of percentage closer when you're on the other side of this orbital. And you really could use a reflective material if that was a concern, or even shades if that was a concern.
It's actually hard for me to wrap my head around the scale of it. That is really insane.
It is huge, and that comes with some material challenge constraints. The issue with a Banks orbital is that there is currently no known material strong enough to hold a Banks orbital together. And the issue is that there's just no chemical bond that's strong enough to hold that type of structure together. There's just physically the atoms don't hold together strong enough. They'll pull apart. Even the carbon-carbon bond, which is one of the strongest bonds we know of right now, it's just not going to do it. Carbon nanotubes, this is orders of magnitude bigger than what those could support. So yes, this is a humongous structure, and the material engineering constraints are the biggest holdup.
Okay. So unless we find a new element that could withstand it, or maybe some kind of a mechanical means, like a living metal.
A living, that sounds interesting. Even a living, like it would still fall apart. But there are some hypothetical materials that could work. Just I see a lot of people throw around the idea of like it's called nuclear pasta. It's the actual stuff that's inside of a neutron star,
Mhm.
and it's effectively made not from the typical chemical bonds you get where electrons and protons interacting with each other, but it's actually made from the neutrons themselves being forced together, and these are interacting through the strong nuclear force instead of the electromagnetic force. So the material inside of a neutron star would be more than strong enough to build something like a Banks orbital, but people seem to gloss over the fact that can only exist in a neutron star, right? Like you can't take it out of a neutron star or it just explodes because it needs that insane gravity.
Well, yeah, I mean, people are talking about using what is essentially the step right before singularity as a building block to an orbital ring. That's
Yeah.
insane.
Yeah, exactly. And I would argue that if you could already control gravity at the point, what you would need to do to keep the nuclear pasta together, then you don't even need the nuclear pasta, because if you can control gravity, you can build one of these structures no problem. If you have artificial gravity, then you can support the structure with that. You don't even need to spin it at that point, and that's the issue. You can build a ring this big, no problem. It's spinning it that creates the issue.
Well, yeah, I mean, if you can manipulate gravity and space time, then yeah, anything's possible.
Yeah, exactly. So
You're also a fifth dimensional being at that point, and and time and space don't mean anything to you. They act as a physical realm.
yeah. To be fair, we don't know if controlling gravity is possible or not. It seems like maybe, maybe not. Who knows? Within the realm of possibility, I would say.
Yeah, of course.
But yeah, so nuclear pasta, I would say, is out for two reasons that I just mentioned. Either you can't control it or make it, or if you can control it or make it, then you don't need it.
Yeah. No, I mean, I just don't see any situation where, there's some things in this world that have a very large do not go near me on them. And a neutron star is one of those.
I don't know if people would say that about black holes, but I talk about using those for everything.
Well, yeah, but you don't talk about using the actual singularity as a
That's
building
fair.
block, and it's always destructive.
That's fair. That's fair. Another hypothetical material that you often see come up when we're talking about building ring worlds this large is something called mag matter.
Okay.
Mag matter is effectively a point-like magnetic monopole. So this is just a positive or just a negative, right? It's not like a normal magnet that has a north and a south. It would just be the north pole or just be the south pole. And typically these are talked about as being smaller than actual protons. And the advantage of that is that they have a stronger electronic charge and they're smaller, so they bind together much stronger than atoms do. So they're taking advantage of that same electromagnetic force, but they're working over much shorter distances and they're much stronger. And
Okay.
again, these would be more than strong enough to build a Banks orbital and to build something this size. We don't really know if it's possible. There are some grand unified theories for the universe that seem to suggest the possibility of mag matter and say that it might exist. But right now, my intuition is this probably isn't a real thing. And even though there are some theories that say that it might be real, those theories themselves are still yet to be proven. So I will say this is something that exists in the pseudo, really reaching space. Maybe this could be possible and it could be used to build something like this. But right now, I wouldn't even say the jury's still out. I would say it seems less likely than more likely.
Yeah. And again, let's say it did exist, right? A matter of a type that was so like and stuck to itself that it could build a structure that no other chemical bond that we know of could have that tensile strength. How do we mine and then manipulate said matter?
Yeah, that's not something you would mind. You would need to create it.
Mhm.
And I think I saw one paper that was talking about how you would need to create basically a proto universe and be able to go back and get it from like when the universe was created. Although that seemed like a kind of a far out there paper.
Yeah, no, a big bang in a jar. Sounds great.
But if you can do that, then yeah, these orbitals are no problem.
Well, yeah, I mean, the reason why I said mine though is because if it does exist, it would be out there somewhere.
Not necessarily. I mean, there's elements that we've created that don't exist out there. A lot of the heavier elements in the periodic table have only ever existed in labs and only ever will exist in labs.
I guess that's fair. Well, because of extreme conditions,
Yeah, pretty
or
much. Yeah.
but I'm just saying the universe out there, it doesn't get much more extreme than that. Now, not to go against that, I'm sure that there are elements that only we know of that exist out there. It's just I feel like if there is something that has been created, that we could create in a lab, there probably would have been some condition at some point where it could have been done.
In the early universe, hence the paper saying you could create like a proto universe and go back and collect it from then.
Of course. Yeah.
Just quickly, yeah. There is a third option
Uh-huh.
that does not require exotic matter.
Okay.
It just requires a lot of regular matter. So what you can do is you can build the Banks orbital, right? Again, this is a spinning ring that would tear itself apart due to just not having the tensile strength. You can then build a secondary ring outside of the spinning ring that is much, much more massive than the spinning ring. And then use that ring to basically squeeze the inner ring together and keep it from flying apart. Now, some key points to understand what's going on here. Firstly, the reason the interior ring wants to fall apart is because it's spinning so fast to simulate 1G gravity. The exterior ring will not be spinning nearly that fast. It might be spinning slightly in the opposite direction to counteract the rotational force, but that's a different argument. It
Right.
doesn't necessarily even need to do that. So it's not spinning, so it's not going to tear itself apart. The forces from the interior ring will be transferred to the exterior ring through something like maybe you could do magnetic bearings, like almost like a maglev train. And then the exterior ring will be much, much thicker than the interior ring to provide the force necessary to hold that ring together. Now, you can't just make the interior ring bigger to support itself because the issue is any mass you add to the interior ring also to like if you try to make it thicker to hold itself together, then that's more mass that's trying to pull itself apart.
Right.
That's why you need the non-spinning ring on the outside. But like I said, you can effectively take a humongous superstructure made from the same material, maybe like carbon composite, carbon nanotubes, and use that to support the inner ring so that you could then build something like a Banks orbital.
Yeah, I mean, that makes sense, I guess, because if it's not spinning, it's not trying to rip itself apart. You could use those counteracting forces to try and stabilize the spinning ring.
Exactly.
Yeah.
And I do think you would probably still spin it, but much, much slower and in the opposite direction as
Mhm.
the other ring, again, just to cancel out that moment of inertia.
Yeah, but like you said in the beginning, material intensive.
Yes.
Uh,
So a Banks orbital would use roughly the mass of a small moon,
mhm.
maybe our moon. But supporting like this, you're talking about using the mass of like the Earth. So that's actually not that crazy. There's a couple of Earth masses worth of material in our solar system, quite a lot of those. So you could potentially take apart the solar system and build a bunch of these Banks orbitals. And mind you, for a Banks orbital, every 42 kilometers thick the ring is
Mhm.
one Earth's worth of living space. And these will probably be thousands and thousands of kilometers wide, tall. So you could get hundreds to thousands of Earth's worth of living space for every single one of these you build. So, yes, you might have to take apart a good chunk of the solar system, but you get a lot of living space for it.
Yeah, I mean, it would have to have an upside like that to justify it. But that does make sense because, you are just using all of that surface area on the inside. And then it has all the other benefits of being able to be manipulated to be essentially whatever we would need it to be.
Yeah. Also, conveniently, it spins so fast that on the ring, you're actually going faster than the escape velocity for our solar system. So if you were to take for example, a spaceship and just let go of it, it has enough escape velocity to leave the entire solar system. So it makes a great launch platform for interstellar ships.
Now, how do you get them on the ring, though?
But you could build them on the orbital, or you have to accelerate them up there anyways, or you could potentially bring it into the center of the ring. And as you bring it to the surface, you can aerobrake it to slow down and catch up with the velocity.
I see. Yeah, because you couldn't just expose an object to a velocity like that. It would just
Yeah, it would be destroyed if you just like tried to land it.
obliterate
Yeah.
it.
So you would need to accelerate up and land.
Yeah, but I mean that would be like incredible. We could be like just launching seeker probes just constantly.
Yeah. Or also, it makes a great thing to intercept ships coming back from interstellar space. They don't need to slow down nearly as much. They just need to slow down enough to match your rim velocity. Then they can just be caught.
There's just like a little pocket for them.
Yep, exactly.
Fly right in.
And then finally, before we close up, we need to address the largest of these structures, the elephant in the galaxy, if you will, which is the Niven ring world. So, mind you, a Niven ring world is basically a Banks orbital scaled up to extreme levels. This is a ring world that is the same diameter as Earth's orbit from the sun. So that's 93 million miles in radius. It takes up the entire Earth's orbit. You get millions of Earth's worth of living space from one of these structures. Now, to answer the quick rundown questions, you would still need orbital mirrors to create a day-night cycle because the entire interior is exposed to the sun.
Mm-hmm.
So if you want a day-night cycle, you need mirrors to do that. And in Larry Niven's Ring World book, that's exactly what they did. Granted, they use like full-on block the sun, release the sun. You would probably have some like transition zone to make a sunrise and sunset effect, but you could do that. There are some obvious issues with building something this large. For one, our neat little trick of trying to reinforce the ring with other material, I think it just becomes infeasible at this point. Not that it was particularly feasible with the Banks orbital, but at this point, I mean, you're mining solar systems worth of mass just to build the support structure for your ring.
Just thinking of like the population that would need to like be alive to justify the production of one of these things is insane.
And this might be one of the only cases where I've said in our interstellar episodes, you would never go to another solar system and bring material back because why? But you would need to do that to build something like this, to be clear.
That's crazy. Like I play Stellaris, they don't have structures of that size in that game.
Yes, so you would need exotic matter. I don't know if mag matter would be strong enough for this. Maybe. I still don't think so. Also, the rim velocity for this is going to be a decent fraction of the speed of light. So if you could release a ship off of the rim of one of these, you have a good interstellar launch system.
Now, just think about like all right, so we just finished building it, right? Like the ring. And now we're like, okay, now we have to start spinning it.
It's going to take a while.
Yeah.
You don't want to just spin this thing at 1G because then it's going to be like destroyed, right?
Yeah. Like the amount of fuel or whatever you're using to get this thing up to velocity, it's just insane.
It is. And then something that hasn't came up with the other structures that I know you mentioned before the show, right? All of these other ring structures, we talk about putting them in orbit of something,
Mhm.
but the Niven ring world is actually enclosing the sun. And something that came up with the ring world books when this was written, that's not a stable system. It will drift into the sun one way or the other. It is a fundamentally non-stable system. And so one of the things you would need to do is you would need to actively control it to keep it from drifting. So you would need some type of thrusters on it to move it around. There's ideas of using solar shades. In Niven's second book, he used Bussard ramjets on the thing to control it because it's spinning so fast that a Bussard ramjet is in the realm of feasibility, but except for they don't really work. They actually slow things down instead of speed them up. We talked about that in our interstellar propulsion episode. But yeah, needless to say, this is not a stable system. So on top of whatever you need to do to get it up to speed, you've got to constantly use it to maintain it and do station keeping.
Yeah. I mean, just like the amount of fuel that you're expelling from this thing, it's a solar system devouring monster, is what it is.
But it's basically the first step of a Dyson swarm or like a Dyson structure made out of rings. So you could absorb a lot of energy from the sun potentially. Although from that distance, you're really absorbing the same energy as this Earth for any given area, but you have a lot of area.
Yeah, you definitely do have a lot of area and then plenty of space to store that energy, but it's like, my God, like just the thought of like this Goliath moving through solar system to solar system, devouring planets and suns to power itself.
It is a bit of a ridiculous one.
Yeah, it's like Independence Day. They're here for us, for our planet.
But yeah, my closing thoughts on like ring structures I just want to touch on. They're interesting. I
Mhm.
could see some of them being possible, maybe even up to a Banks orbital, depending on if we have access to some of these exotic materials in the far future. But in general, I think cylinders make more sense. And I think what you'll end up doing is you'll build ring structures in the beginning and maybe build ring structures to kind of push the bounds on how large you can go in terms of radius and diameter. And then once you hit like a given radius or diameter limit due to material constraint, you'll start to turn it into more of a cylindrical shape and start building more cylinder shapes.
Yeah.
So maybe if you end up with something like a bishop ring, for example, if you can build that, you might decide to just scale it a long ways and make it into a McKendree cylinder versus trying to scale it larger and turn it into something like a Banks orbital because the material constraints just become huge at that point.
I feel like if you just have a ring, right, you're going to get more use out of turning it into a cylinder than turning it into just a bigger ring.
Exactly. Yes.
Because then if you made it into a bigger ring, you would just get more use out of that bigger ring by turning that bigger ring again into a cylinder.
Yes. So I do think cylinders are going to be a much more popular shape than rings for a wide variety of reasons, except for maybe in the early days of building habitats where you just don't need it. Like an O'Neill cylinder is quite a big structure, so maybe a Stanford torus will be a better starting point. Or if you just need a smaller structure for whatever you want.
Yeah. I like the idea that you brought up earlier about using it with companies to have them as like independent manufacturing plants or things like that. Because that way you could have small dedicated rings with temporary living habitats around them, much cheaper to maintain, easier to produce and put out. And then that way it's not affecting an entire station that doesn't need to have that particular half gravity.
So yeah, if you like the idea of using these for maybe manufacturing, then that's something that we can talk about next week when we're talking about colonizing and living in Earth's orbit. What do you think of that?
That's a good idea. I think I will cover that. Yeah. Talk about economy, companies, megastructures on circling around our planet. I think that's a good idea.
And if that sounds interesting to you, check out our next episode when it releases.
Thank you. Bye bye.
Take care.